Maybe we can start, if that's okay for you, Didem Hocam.
Sure, we can.
So hello everyone for the EuroCC-Turkey seminar series. Today, Didem Unat from Koç University with us. So let me briefly introduce her. She completed her bachelor degree from computer science at Boğaziçi University. And upon finishing her degree, she went to University of California, San Diego for her PhD in computer science with Dr. Scott Baden. And she was working on GPU programming, and she developed a Mint programming models and the compiler. And after 2012, she received Luis Alvarez Doctoral Fellowship Award to continue as a postdoctoral researcher in Lawrence Berkeley Natural Lab. And then later she received Marie Curie fellowships and she come back to Turkey, starting as a faculty at Koç University. And more recently, since she's a great scientist, she has been receiving several different awards, both nationally and internationally. One of the recent one is ACM SIG HPC Emerging Woman Leader in Technical Computing. And she is also I think, still the only computer scientist receiving ERC grant in Turkey. So I'm also quite excited for this talk. And thank you very much, Didem Hocam, for being with us today.
Thank you for the introduction and invitation to give this seminar. Today, I'll be talking about some profiling tools that we develop in our group. This research is funded by TÜBİTAK and Newton Fellowship from British Royal Society. So let me share my screen. I'm open to questions during the talk or after the talk if either is fine with me. Okay, I believe you can see my screen, and can you hear me well?
Yes, everything sounds great, and slides are also looking great.
Okay. So today I will be talking about low overhead, but at the same time accurate profiling tools for multi-core architectures. And this is, mainly most of the work done by my students. I'm here to present their scientific contributions to general audience. Okay, so in modern high-performance computing applications or parallel applications, they tend to employ multi-socket, multi-core, many-core CPUs in a node, and we typically program them using MPI plus some threads. MPI stands for here message passing interface, and it is used communication among in a cluster large-scale nodes. But we tend to use OpenMP or other threading libraries such as pthreads for intranode communication within the server or within the multi-core. We tend to use OpenMP or other threading libraries. So we do an explicit inter-process communication via MPI. We do send and receives in a large-scale cluster. But we do implicit inter-thread communication. So the communication happening between threads are kind of implicit, meaning that as a user or the programmer or developer, we don't notice we are doing a communication, but indeed there is communication happening underneath through loads and stores and cache line transfers. So in HPC and in other fields, it's considered that data transfer or the communication is the dominant factor in terms of performance and energy consumption. So any computation you're doing is extremely cheap in terms of performance and energy consumption. What is the bottleneck is the data transfer or the communication in today's HPC applications or any application indeed, because our architectural improvements tend to improve the CPU performance, but as not much as the memory performance or the I/O performance or the communication performance. So data transfers become the bottleneck or the dominant factor. And we need tools to monitor data locality or data movement in the multi-core. There are a number of tools doing this for inter-node communication or a single core, but emergence of multi-core, since we have been using multi-core since 2005 or so, there, even though they have been around, many applications started using them multi-threads, but there's not much tools designed for multi-core architectures. So in order to develop these multi-core architecture profiling tools, there are a number of techniques, and we focus on this technique, which is called precise event sampling. This feature is available in the commodity CPUs. You don't need an extra hardware or you don't need a software change. This is commodity feature. It's available any of the modern multi-core you can purchase from the market. So these extend performance monitoring units, and then which is PMUs. PMUs consists of hardware counters and model-specific registers. These can sample hardware or software events, and in a periodically. So user can say that I want to sample 100,000 instructions, or I want to sample 100,000 loads. I want to monitor specific events in the application so that I can know how much data movement or how much communication is happening. And these are precise. Why? Because we can attribute those hardware sampling these events to instructions causing them, instructions that trigger them. So we can map these into the instruction and analyze that instruction, what's happening. And Intel PAPS is an example, AMD, IBS, PowerPC, MRK, and then ARM recently started supporting precise event sampling in SPEs. Okay, so those are the kind of background. So what do we do in terms of research in my group? This is one of the direction, not only direction, we do other things as well, but one of the direction is we develop system software, namely the profiling tools based on this event sampling feature in the commodity CPUs. The first tool that we developed is ComDetective. This is a communication detection tool for threads. It's first of this kind. And I'll talk about its advanced features later, but this work is published at Supercomputing Conference, which is the most prestigious conference in our field and nominated for Best Student Paper and Best Paper Finalist. And then the next tool is Reuse Tracker. Reuse Tracker is it uses also event sampling feature in the multi-core architectures, but this time it analyzes reuse distance. What is reuse distance? Reuse distance is typically used in compiler analysis, and it's an indication of data locality in your application. This is published at ACM Taco Journal, and it will be presented at High Peak Conference in June. We extended these works while working on ComDetective and Reuse Tracker on Intel and AMD. We realized that there's a drastic difference between their support. So now we are working on AMD versus Intel kind of a paper. There's a very different kind of a paper, and it will shed light on, precise event sampling support and maybe design of precise event sampling in future architectures. So for the sake of time, I will talk about ComDetective and Reuse Tracker, and maybe in another seminar I can talk about AMD versus Intel, but leave this for now out of the scope of this presentation. So let's start with ComDetective. What is ComDetective? So I mentioned that we need communication detection tools, and there are some tools doing this for MPI, message passing, or process level communication. So here in x-axis and y-axis are the process IDs. For example, process 5 is communicating with one of the processes, which is kind of the dark color indicates that they communicate a lot. So for example, this is processor 8. It does a lot of communication. But process 9, it doesn't do any communication at all. So there's already a number of tools indeed for process communication. One of them is EasyTrace, and we generate this metrics. We refer to these as communication metrics for this LULESH application. And you can see it's a pretty looking matrix, and it indicates it's a way to visualize process communication. But on the other hand, for inter-thread communication, there was no accurate good tool that we can show a similar metrics, but this time for inter-thread communication. So that's our contribution. We developed ComDetective, which shows the inter-thread communication between threads. Here are x-axis and y-axis indicate the thread IDs, and in the metrics, dark colors indicate a lot of communication happening between those threads, and lighter colors or the white indicating no communication at all. So here, for example, you can see in the diagonals, there's a lot of activities going on. That means nearest neighbor communication. Or with a distant neighbor, you communicate less. It's a lighter color. It's also indicating, all-to-one communication, like master talking to other threads, which indicates, communication here in this zero, communicating with other threads. So you may wonder why bother inter-thread communication? Why do you need to collect or generate these matrices? Well, we can identify possible sources of performance bottlenecks. In fact, in one of our application, when we generated the communication metrics, we realized that the implementation was wrong because there were two threads communicating with each other which shouldn't communicate, and we go back and fix the code because we have implemented communication layer wrong. And then it can help explain why one threading library is better than the other. So you write one application by using two different threading libraries, and one of them includes much more communication. That means, that library is probably not as optimized as the other one. Or it can guide optimizations. So for example, thread binding. Currently, one of my students is actually working on thread binding. Can we bind the threads to cores in a more optimal way so that we reduce overall communication within the chip? Why we bother doing this? Because again, any data movement you do results in less performance and also increase in power consumption. And then the data structure modification, maybe we have a better way to represent the data so that it leads to less communication. And the false sharing elimination, which I will talk in a second in more detail. And this is in terms of users, but how about hardware designers? Hardware designers are interested in this because they can optimize on-chip network design or their cache coherence protocol based on these profiling tools. Okay, so what are the challenges developing such tool? Why people haven't developed such tools so far? That we are kind of the first doing this. Well, if you consider MPI processes, MPI communication, because explicitly you say, I send data to this process and I receive data from this process. It's very explicit. You tell who is sending the data, who is receiving the data, and then the amount of data they receive. So creating the communication metrics is easy. But on the other hand, inter-thread communication is very implicit because the communication is through cache line movements, and that requires interception to load and stores. So you need to monitor loads and stores in the application. And it can incur, if not carefully designed, it can incur space and time overheads because all the loads and stores can be intercepted, though we choose not to do so. And while monitoring the application, the side effect is you may change the program behavior. That means whatever you're measuring actually is something else, because that's not because you're changing the behavior of the program. You're not measuring actually what you want to measure initially. And this can also scale poorly with the increasing number of threads because of the overhead it brings. And most of the tools that in the prior art we looked at it, they don't consider multi-thread cases, and that's what's important here actually. So ComDetective, on the other hand, it's accurate. We validated its accuracy against several benchmarks, synthetic benchmarks, and HPC applications. It's lightweight because compared to the other methods to measure inter-thread communication or data movement is, they can include 100x slowdown, but in our case, we introduce less than 2x slowdown, both in time and space. It's sampling based. This sampling based, this precise event sampling is readily available in commodity CPU, so you don't need an additional hardware or additional software modifications like OS changes, etc. Those are really intrusive approaches. And it can differentiate different types of communication. I'll again explain what is a true sharing and false sharing. So we identify these separately. And of course, communication matrices generation is valuable, but usually the developers are interested in what objects, what variables in my code, what data structures in my code causing the most communication. So we can attribute communication to program data objects with ComDetective. And we made it open source. You can download and use it, use our benchmarks, or generate communication matrices for your applications. So now let's talk about what is inter-thread communication. This is kind of basics or the background to understand what we're really doing with ComDetective. So let's say you have a thread running on CPU 0 and then another thread running on CPU 1. And note that these CPUs, they have their local caches. This is its local cache, and this is its local cache, and this is our memory. Here, the large is our memory. And note that all the data transfers in the cache or between the memory and cache and between caches happens at the granularity of a cache line. So even when you access one element in this cache line, the hardware will bring entire cache line into your cache or transfer the entire cache line to another CPU. So there is, let's see how the steps when you do a memory access. Let's say it's CPU 0 accesses memory, this data shown in green. When you access the data in memory, it will be brought into your cache, your local cache, and this is where you're accessing. But note that the entire red region is brought into your cache when you access it. And then another thread happens to access the same variable, let's say X. It won't be brought from memory. It will be transferred from cache, the other cache, because this causes less communication. If you go to the memory, it's slower. So what the hardware does is with the cache coherency protocol, it will transfer the cache line from the CPU 0 to CPU 1. So this will be brought from this cache rather than from memory. We refer to these as true sharing. Why true sharing? Because this is the green part is the data that CPU 0 accesses, and similarly CPU 1 accesses the same bytes in the same cache line. There is also false sharing. In the false sharing, however, the CPU 1 accesses a different location in the same cache line. But this data happens to be the same cache line as this one, even though they are different addresses. So this address, the previous address was this one, but the current address is this one. This is called false sharing because these two threads actually don't share the data, but hardware choose to allocate them, map them into the same cache line. So this also causes inter-thread communication which we didn't anticipate initially because this is not really true sharing. This is called false sharing in the literature. It causes data transfer, cache line transfer between these two CPUs. And the good thing in ComDetective is we can generate the communication metrics, but we can split this communication metrics as true sharing metrics and false sharing metrics. So the true sharing metrics is actually, this is what we intended as a communication when we write the parallel program. But the false sharing is really an artifact of how hardware allocated, mapped the data into the cache lines. So it's possible for a programmer to get rid of some of the false sharing so that you only do the true sharing communication, because this is really unnecessary communication that you introduce. Okay, so what are the problems with the existing tools? They don't really do, inter-thread communication, but there's some similar tools that we find that can be comparable to ours. First of all, we realize that observed communication can be very different than expected communication. Expected means I expect this much communication, but in reality, hardware does some optimizations or improvements that the observed communication can be lower. And then we use these as ground truth, and then develop ComDetective and then compare as the ground truth. Ground truth is we measured with some program counters what can be the ground truth for one benchmark, and then we test this with ComDetective and then compare against the ground truth whether we are close to it or not. As you see, we are very close to the ground truth. But another tool, Numalize, it's called Numalize. It's state of the art before our contribution. We initially was using this Numalize to create inter-thread communication matrices, but we realized that our results are not, it's distorted. We are not getting consistent results. And then the reason behind that was the profiling tool itself. Numalize itself is inaccurate, hugely inaccurate, in fact. As you see here, it hugely overcounts the inter-thread communication. So that means if you find a tool online that you want to use, first check whether it's accurate or not, because you may be wasting your time, and we actually wasted quite a bit of time by using Numalize for some profiling for our applications. So you need to check, you need to make sure that it's accurate and it's unable to capture, actual communication pattern in the real hardware. So the other problem with the existing tools is that, let's say they are accurate, but then whether do they introduce time and memory overheads? So there are a couple of tools people develop to measure similar things, but the time overhead and memory overhead is so huge that they are not practical. Why they are not practical? Because they cause 100 times slowdown or 100 times memory overhead, which means that if your application is using, let's say, 2 gigabytes of memory, it will require 100 times more memory to do the profiling. So it will require 200 gigabytes of memory, but that's not practical for real life applications. So that means some of these tools are either really, really slow, or they introduce so much memory overhead that it's not practical to use on real life applications. And there is a third category of tools which they do detecting communication at the memory page level, but these are OS-based approaches, and usually OS-based approaches is intrusive because now you need to update your operating system to be able to use this tool. So there's a question, is ComDetective architecture or OS dependent? So we are using Linux operating system. So we haven't tested these in Windows. So OS dependencies lose any Linux, latest Linux, I should say. Because we are using perf events, I'll talk about the perf event. So OS should have perf events support, and latest Linux distributions, they all support Linux perf event. Whether it's architecture dependent or not, that's if it's x86 microarchitecture, it works. Architecture dependency also comes from the fact that the architecture should have precise event sampling support, and in both in AMD and Intel x86 architectures, we have those after AMD Optron and Intel Nihilium. So again, its architecture dependency is loose because most of the Intel and AMD processor now fall into that category. For ARM, our work is still going on. So for ARM processors, we may change our algorithms slightly, but the general idea is still applicable if the hardware has precise event sampling support. We can easily extend our tool to work on ARM processors as well. Okay, I hope that answered your question. Okay, thank you. So let's continue. So how about the internal design? So internal designs, I will have some animations to go through. It can be a little too low level for some people. So bear with me, and you can ask questions about this, or you can refer to our papers for more details and the algorithm behind this communication detection. So PMUs are spatial registers. They count low-level events such as loads and stores, and they are part of the core. So this is not a, the performance monitoring units are available in commodity CPUs. And then these can sample. That means that we can configure them to trigger and interrupt every n events. After n events, whatever event that is you're configuring, it will trigger and interrupt. It will notify the user application that use the or signal handler that now there is this event. And there is also debug registers in the hardware that we used. Our purpose, you use when you do debugging, you kind of put breakpoints. Those breakpoints are addresses, and these addresses are actually put into these debug registers. Whenever you reach that access or made access to that address, it will send a trap. That trap notifies you that I reached that address or I touched that address in the program. So those are debug registers, and there are 4 of them in Intel processors per core. And there is perf event. That's the Linux part of it. This perf event allows user applications to configure and access PMUs and debug registers. This is a relatively high-level interface for us to configure both PMUs and debug register at the user level. So that means we don't need to go into the kernel level. At the user level, we can use this perf event feature in Linux. And I believe, maybe I'm wrong, but I believe perf event support is since 2014 or so. So it's not very recent, but it's not very old feature. So it's available in Linux distributions. And the perf events, both we can configure PMUs and debug registers. So these parts are part of ComDetective. So far what I talked is part of the hardware or the operating system. So we didn't add anything. Here, our addition is sample handler, which runs when sampling handles. Basically, when there's an interrupt from PMU, it will be handled by our sample handler. And we keep a building board. This is kind of a hash table in memory. We monitor the sample data. I mean, we monitor basically hot addresses. Hot addresses means like the sampled addresses that we put into building board. We monitor about over 100 addresses at a time, for our communication detection. So this is our kind of currently active addresses that we monitor. And the trap handler, this is also part of ComDetective. This one handles the debug registered traps. And let's say there's a thread running on core 0 and another thread running on core 1, and they configure perf events in their respective cores. So how about the workflow? So perf event is configured so that loads and stores to be sampled for communication. Remember, we need to monitor the data movement with that's the loads and stores. And these threads they configure perf event to monitor PMUs and debug registers. And then when there's an interrupt happens in core 0 after n events, we will go ahead and update the building board. So we update here our hash table saying that this is, let's say, a store event or a load event. And we publish this address in the built-in board with a timestamp and thread causing this store and some other information like the cache line, etc., so that we keep track of the recently accessed recent access addresses. And then let's say there's an interrupt happen on core 1. This triggered the event is a store to memory address M1. So we will check the table whether there's a cache line match. Is it the same address that we had previously, and then check whether there's a match. Well, and then if there's a match, we also check whether the entry is recent. That's why we have these timestamps. So these accesses may be far apart. So one of the accesses can be at the beginning of the program by thread 0. Another access might be at the end of towards the end of the program execution, long time passed by thread 1. This is not really inter-thread communication. It may go through the memory. So we are putting a timestamp so that we are identifying this communication if that causes a cache line transfer. In fact, with the tool that I talk about, like normalized tool that related work, they don't have this time notion. That's why they overcount the communication a lot more than it should. And then if these timestamp is recent, we have a way to tell whether it's recent or not. That means we detected communication because the address is matched and then the timestamp was recent, so we update the communication metrics between these two threads. Let's say this is not recent, so that means we replace the address. We delete this entry and then put a fresh entry into the hash table. And another store sample happens, let's say, on another address, M3. If there is no cache line match here, and all the entries are recent, so we discard this entry because there's nothing to update in the hash table. And then we also, let's say we find an entry, then we will set up the debug register so that if there is another address, there's another thread accessing this address, we will be notified. And then again, we will update the communication metrics if there's a trap in the debug register as well. So basically, this is how the workflow, I only explained a couple of scenarios because there are more scenarios. And remember that we have multiple threads and each thread is monitoring some addresses. And then in the hash table has over 100 entries. And then these threads can sample loads or stores, and in the debug register, accesses can be loads or stores. So there are different scenarios, but I explain couple of the scenarios how the workflow is. And here I show, we have a number of benchmarks, but I choose to show only these for the sake of time. This is a snapshot of PARSEC benchmarks. And we are showing 6 of them here in this figure. These considered to be real-life applications. For example, in Black-Scholes, we don't see any inter-thread communication. Well, there was, this is actually financial analysis benchmark, and it's really embarrassing, the parallel. There shouldn't be any inter-thread communication, but one of the work we found, it's an old work, honestly, it's from 2009, but there are actually very few works doing this kind of inter-thread communication measures. And as you see, they hugely overestimated the inter-thread communication, where there shouldn't be any inter-thread communication, but this is, they show the, producer consumer, which is, one CPU generates the data and the other one is using it. It's really kind of the wrong type of representation of the communication. And we did also Coral benchmarks, which are much bigger benchmarks, and I compare against their MPI versions versus thread versions. Some of the thread versions include less communication. Some of the thread versions, on the other hand, introduce a lot more communication compared to their MPI counterparts. And we also use ComDetective to improve the performance of the application. Let's say we profile and get some information about false sharing. Remember, false sharing is kind of a side effect, or how architecture places, the maps, the addresses to data. So by doing padding, you can actually sort of force eliminate some of the false sharing. In fact, we realized that these false sharing actually happen in the pthread library, not the application itself. In the pthread library, mutex and condition variables, how they define the data structure of these pthread library causes false sharing in the application. So it's not the application, but the library it's using. The library that the application uses has false sharing. So we identify the locations of where the false sharing happens, and then added paddings, and this improved 6% improvement in one application and a 13% improvement in another application. Okay, that was ComDetective. Now I briefly talk about reuse tracker. I won't go into detail as much as the ComDetective for the sake of time. So what is reuse distance? Reuse distance is, let's say you have memory accesses like A, B, C, B, D, D, A. These are addresses. So you access A here, and then you previously access A here. That means the time distance is 5, because in between you have made 5 references to memory. But reuse distance is actually 3. Why? Because you access B twice and then D twice. The unique accesses are B, C, and D. That means the reuse distance actually is 3. So after 3 accesses in between, you access the same element, which is A in this case. And then this is in case of one thread. But in multiple threads, that becomes more complicated, because the other thread may access not just you. So let's say you access A and then access A here, but in between, thread 2 accessed A. That means your copy of A is invalidated. So because you transfer the cache line, or this A, from your cache to the other cache of T2, another core, and this causes a cache line invalidation of your copy. Okay, so this is when the caches are private. How about the shared cache? Because cores also share caches. So we extended the private cache reuse distance to shared caches, because shared caches are common. in multi-core architectures. So here, if T1 accesses and then T2 accesses later A, we refer to it as reuse because they are still in the same socket, but they share L3 cache, for example. If they're in different sockets, they don't share a cache. They have, each socket has its own shared cache, L3 cache, then that means this is a cache line invalidation between this access and that access. So comparison with the existing work, in fact, because of its importance, reuse distance analysis is highly studied, but we analyze them in terms of, compare them in terms of time, space, accuracy, the primary method they use, whether they profile private caches and they profile shared caches, whether they consider cache line invalidation and whether they're open source or not. And reuse tracker, which is our contribution, it has reasonable time and space overhead. It has 92% accuracy. It uses these performance monitoring units. And then it has both private and shared cache profiling and cache invalidation. So there's another question. Does ComDetective apply to threads running on CPUs located in separate sockets on the same machine with shared memory? Yes, but at the same time, you can also, threads can run on different CPUs located in the same socket. It doesn't matter whether they're on the different sockets or the same sockets. So think about two threads. You put them in different cores on the same shared memory node. We can measure their inter-thread communication. It's also beneficial to provide inter-thread communication in multiple machines. While in multiple machines, there is not really inter-thread communication. Then you're at process communication, because in multiple machines, then you're using processes to communicate rather than threads. So you use threads within the same multi-core machine. In the multiple machines, you move to processes. They have, because you have distributed address space, not a single address space. If you have a single address space, shared memory address space, then you can profile inter-thread communication. I hope that answers the question. Okay. So, and we made our tool open source. You can download and use it as well. Okay, so the reuse tracker, we have the same sort of the slides for as the ComDetective, so it's fast, it's accurate. Again, we validated against a lot of benchmarks. In fact, I want to mention this, take a minute and then mention this accuracy issue. I think it's very important for a tool to be accurate. And as I mentioned, we use a tool that we wasted several months that it wasn't accurate. But how to verify accuracy is also very important. There is not really, standard benchmarks to measure these. So we developed actually benchmarks, not just to test our tools, but we made them open source so that if someone comes in and then develops reuse tracker plus, let's say it's improved version of reuse tracker or ComDetective plus, they can use the set of benchmarks that we developed to test their accuracy and overheads, etc. I think that's also a contribution. I consider as a contribution because a set of benchmarks for people to test their tools is also important, as well as the tools itself. And it's sampling based, it's multi-threaded. If you look at most of the literature in reuse tracker, they are single thread. They measure reuse distance for single thread, but considering the commonplace usage of multi-core architectures with shared caches, etc., supporting multiple threads, private and shared caches was essential. And we also do code line attribution. Why? We can go back to the source code and then say that where the reuse happens in the source code. This is also important for the end user. Similar to ComDetective, this tool can be downloaded and used under ParCoreLab tools. And we verified accuracy with the ground truth, that's 92%, again, using for 10 PARSEC benchmarks. So I'll move. So in summary, we develop inter-thread communication analyzer, which is ComDetective. It can create this pretty matrices. I really like their pattern. And the reuse record, this is the reuse distance analyzer, which is it's important for the compiler community especially. And we published this ACM TACO this year, and we will be presenting at HighPeak conference. Tools are publicly available, including the benchmarks. You can download the benchmarks as well. And lastly, this work is supported by TÜBİTAK undergrad project node. And then I was also received funding from Royal Society, British Royal Society under the Newton Advanced Fellowship program. Okay, so this is my last slide. I have a group at Koç University, ParCoreLab, Parallel Computing and Parallel and Multicore Computing Group. You can check our website to look at other projects that we are doing. In fact, I have two big projects. One of them is Beyond More. This is the ERC project. It's 1.5 million euros we received for the next 5 years. We are developing novel programming models for heterogeneous systems. And then there's another project, Sparsity, which is a consortium with 6 partners, including Sabancı University and 4 partners from Europe. We are developing algorithms, tools, and novel methods for sparse computation, including graphs and sparse matrices and sparse tensors. So if you're interested in, you can visit our group website or email me if you're interested in internships or graduate programs, master's or PhD programs, or even postdoc. If you're interested in, let us know. That's all from me. I'll be happy to answer your questions. Maybe I can stop sharing my screen, or maybe there will be questions on the slide, so I'll leave it here. Thank you very much.
Thank you very much, Didem Hocam. This was a great presentation, and since you already answered some of the questions in between your slides, so maybe we can ask if there's any other questions from the audience that they want to ask right now.
Is there any other questions?
There's one participant is raising hands.
Fatih is asking.
And there's another one on the Q&A box. So the question in the Q&A is, first, thank you for the presentation. And they are asking, how did you use ComDetective to refactor? Does it reverse the lines of the code or instructions that list the false shares?
That's a good question. So we use ComDetective to identify the objects causing the false sharing. So it can do object attribution. And then we can modify that data structure causing the false sharing. But the refactoring part is manual. I mean, the programmer needs to do it. ComDetective itself doesn't go and modify the code. That's too futuristic, I think. So what ComDetective does is it tells, for example, these we tend to report the type 5 contributor for the communication. We will say, okay, these variables causing false sharing the most. And then as a programmer, you can go ahead and then, for example, change how you define the data structure, do the padding, for example, etc., to change the data structure in the application. Does that make sense? No? Yes? Yes, okay. And there was another question, I think.
Yeah, is it possible to
Fatih?
unmute yourself, Fatih?
Fatih, we cannot hear you.
We can turn on the microphone of the participants. If you have a questions, you can write it down on the Q&A feature.
Fatih, can you write it down, your question?
Yes, in the Q&A section. Thank you.
He's asking, as I understand, the ComDetective profile applications and then reports the profiling at the end of the execution. So it's an offline profiler at the moment. But is there any obstacle modifying it into an online profiler?
That's a good point. Yes, we are offline profiler. We kind of report the overall, cumulative communication results. But while the application is running, actually, we are creating this metrics in the background, right? I mean, we are populating the metrics, but we report at the end. If as a user or a tool developer, if you're interested in, showing the communication metrics as it's populated, it's completely possible. Because as I showed in my slides here, let me, for example, we update the communication metrics regularly. So what you can do online as an online profiler, you dump this into your monitoring tool regularly, every, I don't know, iteration or every second, some frequency that you define, and update its visual content every with some predefined or regular intervals, then it's completely possible. I hope that answered your question as well. Yeah, I mean, this matrix is dumped at the end, but we are holding the, we are creating it while we are profiling the application.
And I should also thank Sevil Hanım for sharing the ParCoreLab websites and the contact information for Didem Hoca.
Yes.
So I believe she has openings in her lab for different positions. So if you are interested, I think we should definitely keep in touch with her.
Yes, thank you. Thank you very much for the invitation. And I see a number of people are asking questions. That's a good sign that they are interested in the topic. I'm aware that this is a kind of very low level fundamental CS, fundamental operating system and architecture, kind of the combination of computer architecture and operating system topic. Some people really like the system related research. We also have other type of research in directions of more on the application side or the programming model design or compiler side. So if they're interested, they can contact me anytime. Thank you for your time as well, Onur. And thank you for hosting me. Maybe I'll give another seminar later this year or in the summer. We'll see, on a different topic.
That will be great. Looking forward to it.
Okay, thank you.
Have a nice day, and thank you very much for participating in the EuroCC Turkey's seminar series.